Hello everyone. Today I'm introduce our new work, Defending Against Traffic Analysis Attacks with Flexible In-Network Obfuscation. And my name is Guorui. Traffic analysis attacks means that the attacker can use side channel information of the encrypted traffic, for example, the packet size, direction, timing, IP addresses, to predict user activities by a trained DNN. After this analysis, the attacker can do many malicious activities. For example, you can identify when and which website you are most interested so that to conduct a targeted phishing. Also, you can identify if there have some vulnerable IoT devices in your home so that it can hijack for surveillance. Currently, they have many defense solutions, and their workflow is depicted in this figure. The key points of this figure is that first, there is an encrypted tunnel. This tunnel will hide the obfuscation details, for example, padding packets or insert fake packets. Also, you will covering the real visited IP addresses because the user will first connect to the proxy server. Also, the other point is that this work needs the obfuscators to work in pairs. For example, OBF-A at the user side packets, and then OBF-B in the proxy server remove the paddings and recover the clean traffic. Nonetheless, this workflow has some shortcomings. First, it is inflexible because the proxy server usually are maintained by the commercial third-party organizations, for example, the NordVPN company. It is very difficult for these third-party organizations to cooperate with us and installed OBF-B in their network to help us obfuscation. Also, some solutions choose to pad packets with human-designed strategies, and these strategies may not be well optimized, which will increase the bandwidth overhead and thus delay the user visiting lattice. So in this work, we would like to redesign this workflow to this one, and we call it Securitas. In Securitas, it fits three important properties. First, OBF-A in the user network can change different types of the section information, and the encrypted kernel also will hide IP addresses. And second, we would like to implement OBF-A as an in-network obfuscation for fast network traffic processing, and the processing is guided by a strategy that learned from a trained neural agent so as to optimize the bandwidth overhead. Third, it is a flexible framework because there have no OBF-B on the internet, so there is no need for the third party to cooperate with us to perform the obfuscation. However, when we try to design this framework, we meet three challenges. First, without OBF-B, how could we de-obfuscate the outbound traffic? Outbound means from the user to the server, and also we may not obfuscate the inbound traffic from the server to the user because there's no OBF-B on the other side to help us. Second, given that in the real world, there is the attacker The DNN of the attacker is unknown to us, and obfuscation operations like padding packets, inserting packets are mathematically non-differentiable. So, how could we train the obfuscation strategy through a neural network without these conditions? Third, how to implement OBFA on the in the network, especially current hubs. There are so many programmable devices on the network, like Tofino, FPGA, and other software versions. So these devices may follow different P4 paradigms. How could we make our solution be generalized to these devices? To solve these challenges, we make the following contributions. First, we design new obfuscation operations, which are based on the well-supported IP behaviors like packet fragmentation and TTL properties. Second, instead of the normal gradients, we use the policy gradients derived from the proxy DNN. The proxy DNN is to act as the attack DNN to give us the feedback for training. And also we design a logs to optimize and train the neural network so that it can output the desired strategy. Third, in order to make our solution more generalized, we unified our obfuscation operations in a standard way. We call it clone then modified, which means that no matter what we used, like fragment or GTL packets, they can both implement it by first clone and then modify the corresponding packets. Okay, now first we need to detail the obfuscation operations. The first one is the packet fragmentation. It is observed that routers fragment packets when they are forwarding the packets to the next hop, if the next hop has a smaller NTU. Therefore, we can split an original packet to two smaller pieces and modify their headers to be legal again. And then, as one packet is split to two, it will change the observed features like size or directions of the attackers. And how do we decide to the length or the byte size of these two fragments? It is based on our strategy. This strategy have n elements, and each one is corresponded to an outbound packet. And if the outbound packet has L bytes, we will split this packet to two pieces with A bytes and L minus A bytes. However, this operation has a shortcoming. That's because OBFA is deployed in the user network, so we can only fragment the outbound traffic. Therefore, in order to process the inbound traffic, we propose the second operation. It is the small TTL packet insertion. When a packet's TTL is reduced to 0, routers will discard this packet and probabilistically send back ICMP reply to the sender. And this figure shows how we use it to mislead the attacker. The user may only send one packet, and our solution sends another small TTL1. And this small TTL1 will be expired in the middle of the network and trigger an ICMP reply back to return. And the real server may also send a real packet back. In this way, the attacker will see 4 packets instead of 2. And because this attacker is above the encrypted tunnel, so it cannot know that this is the ICMP reply or a normal packet. And in this operation, the strategy will decide the bytes of the packets that we insert after the corresponding packet P. However, if we insert new packet into the network, they will introduce more extra bytes. In this example, by sending 2 packets, we already introduced 2 new packets. This will burden the bandwidth overhead. Therefore, we need to make a trade-off between fragmentation and small-scale packet insertion, and we use a learning technique. At first, we built a neural agent. It is mainly based on a LSTM model. This model will output the elements in the strategy. Once it outputs a strategy, this strategy is applied to the real packet sequence and then generates an obfuscated one. This obfuscated one is sent to the proxy DNN, which is act as the attacker to give us its confidence on predict the obfuscated sequence correctly. And we also consider the extra bytes we introduced. And also, as here this is a proxy DNN, so we need to guarantee that the similarity between before and after the obfuscation is small, so that this obfuscated packet sequence can be also work on the unknown attacker. And after we design these 3 terms, we have our loss function. This loss function will be used in the proxy gradient generation. And then we use this policy gradient to update the agent so as to minimize the loss. Once we have the optimized strategy, we will have obfuscation as follows. It has 3 core logics. At first, we allow the element in the strategy to be 0. 0 means that we do nothing on the corresponding packet. This is helpful because 0 makes us can do variable length and non-continuous obfuscation, so as to strengthen our defense. And if the element is not 0, we may do fragmentation or small-scale packet insertion. And the choice of these 2 operations is based on the preference parameter PR. This parameter will every time we will generate a random variable and compare it with the preference variable parameter, so as to choose one of these 2 operations for the packet. And then these 3 logic will be implemented in the portable switch architecture in P4, and they are unified in the clone then modify minor as we discussed. In this minor, the ingress pipeline will be responsive to count the packet and then match the entry of the strategy for the obfuscation operation, and the PRE will clone the packets from 1 to 2, and then these 2 packets will go to the egress pipeline for the modification. Here we modify either the original or the cloned packet to be a legal fragment or a legal inserted fake packet. And we have to thorough experiments. At first is the dataset test, where we consider 3 attack scenarios, 5 solar defense solution, and 9 attack DNNs. And in the synthetic traffic test, we have hardware test bed of Tofino and FPGA, high-speed traffic from 20 to 100 gigabits per second. And in the real-world test, we visit 20 web servers and 2 IoT hubs through the commercial NordVPN proxy server, and we test our solution in both hardware and software. This is the dataset results. And in the aspect of attack evasion, Securitas reduced attack accuracy by 96%. And in the bandwidth overhead, Securitas is 42 times lower compared to the current in-network data. And in the synthetic traffic test, we have Tofino testbed and FPGA testbed. Through these two testbeds, we have the following results. In Tofino, the process of the real traffic throughput is 95 gigabits per second and is 75 gigabits per second in FPGA. And the website load time is 1.8 times faster than data. In the real-world test, we use Tofino testbed and the software testbed. And these two testbeds show that we visit the 26 websites we visit. They have over 70% of them has a small delay, which is smaller than 0.15 seconds. And in the IO and in the software testbed, the IoT devices connect to the IoT hub has an extra latency from 0.2 to 0.3 seconds. In conclusion, in this paper, we propose Securitas. This is an in-network obfuscator, which is flexible and has low overhead when defend against the traffic analysis attacks. And Securitas use the packet fragmentation, small TTL packet insertion, and the ICMP replies sent by the node on the internet to do its obfuscation. And Securitas attack evasion and the bandwidth overhead is optimized through the learning techniques like training the LSTM model. And we have a well-before implementation, which makes Securitas applicable to both hardware and software data plan devices. Finally, we do thorough experiments on datasets and real world and confirm that our security is better than the current solutions. Finally, thank you for your attention. And if you have any questions, please email me or you can check our code on GitHub.